We usually spend so much time talking about chemical bonds, the stuff that actually builds molecules, but today we're zooming out a bit. We're going to uncover what I like to call the silent architects of nature. These are the invisible, kind of secretive forces that actually control the physical and biological world around us. We're looking at what happens after the molecules are already built.
Think about a couple of everyday mysteries for a second. Why does water boil at 100 degrees Celsius, while methane, which is a molecule of very similar size by the way, boils at a freezing -161.5 degrees? Or, here's a wild one, how does a gecko support its entire body weight hanging from a single toe on vertical glass with absolutely no glue or suction? Now what's really fascinating here is that the chemical bonds themselves inside those molecules, they literally cannot explain this. To find the answer, we have to look one level up.
So to solve these mysteries, we really need to nail down a core distinction, the difference between intramolecular forces and intermolecular forces. Intramolecular forces are the super strong covalent or ionic bonds inside a molecule. They completely dictate what a molecule is. But intermolecular forces, or IMFs, are the attractions between different molecules. They decide how those molecules behave together as a crowd. Now, generally speaking, the bonds inside a molecule are way stronger, like 10 to 20 times stronger than the forces between them. But, as we're going to see, these weaker intermolecular forces, they are absolutely mighty in numbers.
Okay, a great way to picture these interactions is like a strength ladder, and we're basically going to climb it together. We'll start way down at the weakest end with London dispersion forces, move up a rung to dipole-dipole forces, and finally hit the strongest common IMF, hydrogen bonding. And as we climb, we'll see exactly how these individually weak, tiny forces sum together into this immense collective power.
So, starting at the bottom of the ladder, London dispersion forces. Now, electrons are never perfectly still, right? They're always buzzing around. So at any given split second, the electron cloud around a molecule might shift and just by pure statistical chance, bunch up on one side. This creates a fleeting temporary dipole. It's just a momentary imbalance of charge. Now, it only exists for a tiny fraction of a nanosecond, but it induces a matching shift in a neighbor, and suddenly, snap, they attract. And the craziest part, this force is present in literally all atoms and molecules, no exceptions.
To really get this, let's compare two nonpolar molecules that rely entirely on dispersion forces, methane and octane. Methane is tiny. It only has 4 electrons worth of polarizable surface, meaning its dispersion forces are super weak, so it's a gas at room temperature. But octane? It has a much larger electron cloud, way more surface area. Simply having more electrons and more surface contact drastically multiplies these dispersion forces. And that is exactly why octane, the main stuff in gasoline, is a liquid while methane is a gas.
Which brings us right back to our gecko. A gecko's feet are essentially molecular Velcro. They're covered in hundreds of thousands of microscopic hairs called setae, which branch out further into millions of tiny little tips called spatulae. Every single tiny spatula generates a vanishingly small London dispersion force when it hits the glass. But, and here's the magic, when you multiply that tiny force across millions of contact points, they add up to a collective force strong enough to let a gecko literally hang from the ceiling. It's just pure additive physics.
All right, stepping up to the next rung on our ladder, we have molecules that act exactly like tiny little bar magnets lining up north to south. These are dipole-dipole forces. Now, unlike the totally random fleeting shifts we just talked about, some molecules have a permanent, built-in charge separation. Because some atoms are just better at pulling electrons toward themselves, these polar molecules end up with a permanent positive end and a permanent negative end. This creates a really steady, predictable attraction between neighbors.
And you can see the real-world impact of this everywhere. Take hydrogen chloride. Because chlorine hogs the electrons from hydrogen, the molecule has a permanent dipole. That gives it a much higher boiling point than similar nonpolar molecules. Or think about acetone. That polar carbonyl group creates a permanent dipole, which makes it an absolutely fantastic solvent. It's the exact reason acetone can break down nail polish and mix so perfectly with other polar things like water.
Okay, now we reach the absolute star of the show, hydrogen bonding. It is exceptionally strong, and here's why. When hydrogen covalently bonds to a super greedy atom, specifically nitrogen, oxygen, or fluorine, its electrons get pulled away so aggressively that the poor hydrogen nucleus is left almost totally exposed. It acts like a bare, positively charged proton. This creates the absolute strongest commonly encountered intermolecular force. Honestly, it's so strong and unique, it's basically in a category of its own.
And the effects of hydrogen bonding are literally world-shaping.
I mean, it's the specific reason ice floats. As water cools and freezes, those incredibly strong hydrogen bonds lock the molecules into a rigid, open hexagonal pattern. Because of all that open space in the lattice, ice is actually less dense than liquid water. And thank goodness for that, right? This geometry means lakes and oceans freeze from the top down, creating this insulating blanket of ice that lets entire aquatic ecosystems survive the freezing winter down below.
And it goes way beyond just floating ice. These IMFs dictate so many everyday properties. Stronger IMFs require way more thermal energy to break apart, which is why water boils at 100 degrees, while hydrogen sulfide, with its weaker forces, boils all the way down at -60. It's wild to think that these invisible interactions are the exact reason honey pours so slowly. Its massive hydrogen bonding networks resist flowing, and why you can carefully rest a paperclip on water, right on that elastic skin of surface tension.
Now, you've definitely heard the rule, like dissolves like. Well, let's look at water and oil. Water has this tight, highly organized network of those strong hydrogen bonds. Oil, though, it's just long hydrocarbon chains hanging out together using those weak dispersion forces we started with. Breaking apart water's super strong network just to let oil's weak forces in, energetically, it's a terrible deal. They just don't want to break up their tight network, which is exactly why your oil and vinegar salad dressing separates the second you set it down.
This also perfectly explains vapor pressure. Substances with weaker IMFs evaporate much more easily because it takes way less energy for the molecules to just fly away from their neighbors. Ever wonder why rubbing alcohol feels instantly freezing cold on your skin? Even though it does have hydrogen bonds, they're moderate. They're nowhere near as extensive as water's network, so it escapes the liquid state really quickly, rapidly pulling the heat right off your skin as it vaporizes.
So, let's zoom all the way out to the grand scale of life itself. Our very biological architecture relies on these forces being strong enough to hold shape, but flexible enough to actually do work. DNA uses hydrogen bonds to hold its strands together. Proteins fold into these incredibly complex shapes using them. Even cell membranes use dispersion forces to organize their critical lipid bilayers. Biology is totally dependent on this delicate balance, forces that can hold things tightly, but can also easily let go when a cell needs to function.
Actually, let's look a little closer at that DNA example because it is just mind-blowing. The two strands of the famous DNA double helix, they are not held together by permanent covalent bonds. Adenine and thymine share 2 hydrogen bonds, guanine and cytosine share 3. Why does that matter? Because if our DNA was locked together by permanent covalent bonds, the genome could never be unzipped, read, or copied. Our entire existence depends on a force that is strong enough to preserve our genetic code, but crucially weak enough to be unzipped by enzymes.
It really has been an amazing journey up this strength ladder today, and I want to leave you with one final powerful thought to chew on the next time you watch a glass of ice water or think about your own cells dividing. Covalent bonds build molecules, but intermolecular forces build worlds. I think that perfectly sums up everything we've uncovered. These forces might be individually weak, but collectively they write the rules of our reality. So what invisible forces are secretly building your world? Thanks for joining me for this explainer. Keep asking those big questions, and I'll catch you in the next one.